When I was asked what I would like to talk about at this summer school, I thought about some line of work of mine or some topic that some line of work of mine touched a few years ago, maybe 4 or 5 years ago, and that was this concept of smoothing. So let me maybe start. Yesterday in Daniele's talk, we heard that LWE is essentially an interface to lattice cryptography, right? So in the definition of LWE, we're going to look at this in a moment, you basically don't really see a lattice. You see matrices over ZQ and error vectors, but it looks more like a discrete coding problem than what is really a lattice problem. So what LWE does, it connects the worst case hardness of lattices with, let's say, an instrument or some assumption that is handy to build cryptographic schemes from. And this is LWE. And really the cool thing is when you use LWE, you can kind of do lattice crypto without really fully understanding lattices. And I think this is true for most of us, except for Daniele, Chris, and maybe Alon, who started working in this area, that when we first dipped our toes into this, we, at least this is true for me, only had a very tenuous understanding what to do with lattices, but then you see this LWE assumption, and it looks kind of friendly, right? And then you can ask yourself, what can you do with this, right? And in fact, it was really only with the introduction of Regev's LWE that lattice cryptography picked up speed, and we saw amazing developments like constructions of FHE schemes, constructions of ABE schemes, the things that Shweta and Hotek presented yesterday and today. And but going back maybe to what Daniele said, namely sort of when we're talking about LWE, there's always these Gaussians, right? And they're a somewhat, should say, natural error distribution, and the reason they are used, at least according to Daniele, is because they're somewhat easy to analyze. They have very nice Fourier properties. However, my message in this talk is kind of going to be there interesting beyond establishing worst case hardness of these handy problems like LWE. Gaussians provide very beautiful security features that we currently don't know how to achieve with other distributions. Okay, good. Then a quick overview over this talk. First, I'm gonna talk about some basic tools I think that we've also heard of, and that's a technique called drowning, and something called the leftover hash lemma, that are very generic tools that work for non-Gaussian distributions. And what I'm then moving over to is to talk about some more refined tools like singular value analysis and what it has to do with Gaussians, and a technique called smoothing. Great, and as applications of this, I'm briefly going to discuss FHE circuit privacy. So Hotek and Shweta have already introduced fully homomorphic encryption, in particular the GSW fully homomorphic encryption scheme. And I'm going to discuss a notion called circuit privacy, right? Typically for LWE, when we do encrypted computations, we want to, the main goal is to hide the input, but kind of hiding what computation is performed on this input is sometimes a second order concern, but there are applications for which this is really should be on par with hiding the input. And for this you need a property called circuit privacy. Then I'm going to talk about something slightly different, namely entropic LWE. Right? Typically, we assume that instances of LWE are generated flawlessly. As a matter of fact, that secrets, the secret of LWE is drawn from a uniform distribution, and one may ask what happens if we replace this uniform distribution with a distribution that is only somewhat random, but not uniform. But okay, now let's quickly recap the learning with errors problem, which we saw already a few times, and I'm only going to talk about the so-called decisional version of this problem. There's also the search LWE problem, but in the decisional LWE problem, we're going to be given such a matrix A of sizes m times n. Whoa, what's this mean? M times n. So with m columns and n rows. Ready here, this matrix is defined over ZQ, and we're going to be given such a sample vector S times A plus E, where our S is a uniformly random chosen vector from ZQ to the N, and E is a vector chosen from some error distribution. So in the basic definition of LWE, this error vector just follows some distribution. An important point for correctness is that this distribution is, we say, short, or has a small support, or the components of this vector are short in Euclidean norm. Okay, and the decisional LWE problem postulates that this pair A and SA plus E looks computationally indistinguishable from, well, A stays the same, but this SA plus E is supposed to, or we conjecture this to look uniform, right? So even though SA plus E is a vector that is very close to the row span of A. In fact, as again was said already multiple times, if we left out this error, recovering S would just be simple linear algebra, right? By a Gaussian elimination, we could just recover this S, and this couldn't possibly be indistinguishable from a uniformly random vector. And the hardness really comes from adding in this vector. Okay, but we've also heard that learning with errors with a Gaussian error distribution is something special because it enjoys a worst to average case connection, meaning in the seminal work of Regev, there was a so-called worst to average case reduction from the shortest independent vectors problem, which I'm not going to reintroduce, to LWE, which sort of made essential use of some of these features of these Gaussian distributions. There were later two works by Peikert and Rappe-Niemirska et al., which provided a classical worst-case hardness reduction. So Regev's reduction had a quantum step, as we already heard, but this alternative reduction is to a different lattice problem, to the gap shortest vector problem, and required somewhat slightly different techniques and doesn't provide just the same nice parameters. Good, but an important, let's say, quantity that comes out of these worst to average case reduction is the so-called modulo to noise ratio of the LPN problem, which corresponds to the approximation factor of the underlying worst case lattice problems, right? So I said we're working over ZQ, and now this error distribution chi, if it's a Gaussian, it's parameterized by some parameter sigma, essentially a standard deviation of the, or scaled standard, slightly scaled standard deviation of this Gaussian, and it kind of tells us how much trust we should have in this LWE instance that we have, right? The rule of thumb is the smaller this modulus to noise ratio, the better, right? So if we need at least a small polynomial in the security parameter, something like lambda squared. So Q needs to be, essentially that means Q needs to be bigger than sigma for this problem to be useful. But for some applications, we need to make Q much larger than sigma, in fact, super polynomially larger, right? And this kind of corresponds to a worse LWE instance. In fact, if we make this modulus to noise ratio exponentially big, we're going to get into a regime where lattice algorithms such as LLL can efficiently break this problem. Okay, so with that in mind, let's talk about basic tools. And the first thing that we, I think, also already heard of from Shweta is a technique called drowning, sometimes called flooding, sometimes called smudging. So what is this? Let's say we give ourselves a distribution chi. For now, it's just one-dimensional, right? And we ask this chi to be symmetric and on the positive axis to be monotonously decreasing, right? So it's just dropping off. It doesn't have any bumps or whatnot. Now let's take ourselves a sample E from such a distribution chi and an offset T. And this basic drowning lemma that I'm going to show you says that if I take E and a slight shift of E by this parameter T, then the statistical distance, I'm going to define this in just a second, of these two distributions, E and a small shift of E by this T, can be bounded by the probability that E is, let's say, lies in a small strip around 0 from minus T over 2 to T over 2. And really the bottom line is that if we have an error distribution chi, then if we get a good anti-concentration bound for chi, so if chi doesn't concentrate too much around 0, then this distribution can hide small shifts T. Good. Now, this can be generalized to convex combinations of distributions like this, but I would like to keep this simple. So quickly, the statistical distance between two distributions that are supported on the same domain, we've seen that already, is just the sum of the absolute values of the pointwise differences of the individual probabilities, right? So if we take ourselves a distribution, in this case a Gaussian, and drawn in blue, and a slight shift of it drawn in orange, then the statistical distance corresponds essentially to the area in between these two curves. Okay, and now I would like to show that the area between these two curves is essentially, yeah, the probability that the blue one lands in a small strip. So first I said this chi is supposed to be symmetric, right? So what happens around this crossover point here, left and right of it is the same. So since this distribution is symmetric, it suffices to just look what happens on one side of this. Okay, now of course, now I'm only looking at half the statistical distance, so I need to then essentially correct with a factor of 2, but as a matter of fact, the definition I gave here for statistical distance, there's a factor of 1/2 missing in front of it, but okay. So we're still looking at this red area, and the way we can compute it is we can look at the entire area under the orange curve, right of this red line, minus the entire area under the blue curve, right of this red line, right? So this is still the area in between these two probability distributions. And now what I'm going to do is I'm going to take the blue area and just shift it a little bit to the right. Right? It's still the same area. Now it's sort of clings to the red curve instead of the blue curve, but the difference between those two is still the same. Okay, and now if I compute the difference, it's really just the area under the orange curve, which is in between these two red lines. And since the blue curve is the same as the orange one, I can shift this back here and just look at this area in the blue curve, and there I have it, right? All the none of the operations that I did changed the area, so it's still the same. So I can bound the statistical distance between this distribution and a shift of it just by looking at the probability mass that concentrates around 0. Okay, and what does this concretely mean? So there's two very popular choices for distributions that are being used to drown other distribution, and the first one is a rectangular distribution, right? This is just for simplicity of how you compute this and of analysis, and here the probability that the rectangular distribution of width r lands in this small strip of width t around 0 is just t divided by r. And for Gaussian distributions, you can do something similar. Here you cannot compute it exactly. You could compute it exactly, but you can approximate it very nicely. If this t is small, you're going to get a good approximation by t divided by sigma for this for the area under this thin strip. Okay, but good. Now we have bounds for statistical distances of some distribution or some sample E of a distribution chi and a shift of E, and it says t over r and t over sigma. And typically, we want statistical distances in crypto to be negligible, right? So for t over r to be negligible, r must be super polynomially larger than t. And the same is, of course, true for sigma. So that means in order to hide any information with this drowning technique, we need very wide drowning distributions, which, of course, is from a, let's say, both from a theoretical perspective, this is not so great, because now you need, when you use this in conjunction with LWE, you will have to use a super polynomial modulus to noise regime. This is now unavoidable, right? Meaning that you have to use a stronger LWE assumption. And from a practical perspective, you from a practical perspective, you end up with worse parameters, larger ciphertexts in your LWE instances, and just drawbacks. Okay, and I will very quickly talk about leftover hashing. We've also heard that before from I think both from Daniele and from Shweta. So quickly, the min entropy of a distribution is essentially just the log guessability. So you're taking your distribution and look at by the way, if you have any questions, just interrupt me. If you have any distribution like a Gaussian, it just suffices to look at the peak of such a distribution and look at the probability there and take the logarithm of it. Since this is smaller than, since this probability is smaller or equal than 1, you have to put a minus in front of the logarithm to make this positive. Okay, so for simplicity, let's just assume our modulus Q is prime. You can also do things for non-prime Q, but it gets more messy. And let's say we have a distribution X supported on ZQ to the M with the property that this min entropy is bigger than n times log Q plus 2 times log 1 over epsilon. Epsilon is just a statistical distance parameter. This can be anything sub-polynomial, so to speak, or anything slightly negligible for this to be useful. And this also holds for conditional min entropy. I only wrote it here with proper min entropy, but also this also holds with conditional min entropy. And now let's take ourselves a uniformly random ZQ matrix with dimensions n times q. Then the leftover hash lemma says that a and a times x, the hash value of x, so to speak, is epsilon close, and if epsilon is negligible, it's statistically close to a comma u for a uniformly random u. So this hashing operation completely smoothes out such a non-uniform but high min entropy distribution X. Okay, and now, so we've seen this in essentially security proof of the RAGEF encryption scheme and also the GSW encryption scheme. And here we sort of have our first application of this drowning technique. So let's quickly recall how GSW encryption works. The public key is a matrix A. The secret key is a vector S, and ciphertexts are matrices A times R plus M times G, where G is this often discussed gadget matrix, right? And we need that our R is short matrix or sampled from a short distribution. Whoops. And there's our R. And this G is our gadget matrix. So when it comes to decryption, we just take a vector composed of S minus S transpose and 1 and multiply it with C. And again, we've seen this before. This gives us E transpose, where if we go back, E is, no, I misclicked. E is, so the public key, this matrix A consists of a uniform matrix A prime and an LWE sample S times A prime plus E. And when we decrypt, this E shows up again, namely in a product with this R. Okay, and let's take ourselves two ciphertexts, C1 and C2. C1 encrypts a message M1, C2 encrypts a message M2. Then the simplest thing to do is just homomorphic addition, where we just have to add these two ciphertext matrices, and just by writing out their explicit forms, we can rephrase this as A times R1 plus R2 plus M1 plus M2 times G. So if R1 and R2 were short, then R1 and R1 plus R2 is still short, though a bit longer, right? We'd expect it, the length of R1 and R2 to roughly double here, or to at most double. Good. And the ciphertext encrypts M1 plus M2 now. When it comes to homomorphic multiplication, we've used this binary decomposition operator, typically written as G inverse. And we compute C1 times G inverse of C2. This can also be done the other way around, C2 times G inverse of C1, but yeah, we have to decide which way around to do that. And if we write this out now, the error, or this new matrix R that we get here looks a little bit more complicated, right? We have this R1 times G inverse of C2 plus M1 R2, but R1 is short, G inverse of C2 is a binary matrix, thus also short, so their product is also still short, and M1, let's say, is either 0 or 1, so M1 times R2 is also still short, and it encrypts the product of M1 and M2. But the important thing now is such a ciphertext C star, whatever homomorphic operations we're doing, we've done on a few input ciphertexts. So on the one hand side, we can easily bound the growth of the norm of this R, so it only grows moderately, but okay, this R prime should be R star. This R star is now far from random, right? So for someone who's in possession of the secret key, and let's say knew what the randomnesses are used in the input ciphertexts were, this R in the output ciphertext is anything but random. It, as a matter of fact, is completely non-random because the way I've defined homomorphic operations here doesn't use any additional randomness, right? Randomness doesn't come out of thin air. Either we inject it somewhere or nothing random happens. So bottom line, this R, or information about this R star, can be recovered by someone who's in possession of the secret key, or alternatively is unbounded. So we're looking at, we want to look at statistical security here. So we want to have security against adversaries who have unlimited computational power. And from such an R star, I can just deduce information on what kind of computations were performed on such a ciphertext. And so circuit privacy is, I'm not going to define this explicitly, but this property asks homomorphically evaluated or computed ciphertext to look statistically like fresh encryptions, right? And we've seen with this vanilla GSW scheme, this is far from it. And in order to hide some residual information which accumulates in this R, we have to apply some ciphertext sanitation strategy. And so the first idea is just what comes to mind and what one would do in group-based encryption schemes like El-Gamal, add an encryption of 0, right? Sample a fresh encryption of 0 and add it on top of such a ciphertext C star. And an encryption of 0 in GSW is just A times R for a fresh R. Okay, let's see how well this does. We know that our public key A is of the form A prime and S times A prime plus E. So the last row, again, is not uniform, but sort of close to the row span of this A prime. And if we just look at the first component now, right, anything that happens up here, so if we let's say this is the first component and this is the second component here. So anything that happens with the first component, this is just A prime times R. And yeah, by the leftover hash lemma, R has sufficient entropy. This A prime times R is statistically close to uniform. Great, and hence also this, since A prime times R is uniform, so any shift of it. So A prime times R star plus A prime times R is also statistically close to uniform. However, if we look at the second component of this new re-randomized ciphertext, and write it out, we get S times A prime R star plus A prime R. So this is this part that we already know to be uniform, plus E transpose times R star plus R. And the first part is fine, but this second component, E transpose times R star plus R, this still leaks information about R, because about R star, because we said this R is in the basic GSW scheme just a random 0-1 matrix, so there's no hope that this R could actually drown out R star. So there's still information about our R star in this ciphertext, and this E transpose times R star plus R still leaks information about R star, and the way to get rid of that is to additionally introduce a drowning term. Here I wrote D, but this should not be D, this should just be utility. I changed it everywhere, but there. Good. Yes, question?
I have a question, because R is uniformly random.
No,
so
no. It's R is a uniform 0-1 matrix. So it's a short matrix. It's just consists of zeros and ones. So it's not uniform over ZQ.
Ah, so this is why it's not a kind of one-time pad for R star.
Exactly.
Thanks.
So it's short, and it's not a one-time pad, and it cannot drown. In fact, drowning is almost something like a one-time pad for let's say modulo 0 distributions, or for distributions on infinite domains. But okay. Good. So now let's introduce this an additional drowning term to this re-randomized ciphertext C prime, which is just a fresh matrix, which is 0 on its upper part, and just the last row of the ciphertext down here is an E tilde, and this E tilde is chosen from a distribution wide enough to drown out this E transpose, this vector E transpose R star plus R. So we know E is short, R star is short, R is short, so this vector overall is short, right? So this vector takes the role of what I call this shift T in this drowning lemma. And first component of the ciphertext, nothing changes because of the 0, but now in the second part, we still have this S transpose A prime R star plus A prime R plus this term that we want to get rid of, now plus this E tilde, and now we use this Drowning lemma to say that E tilde plus this is statistically close to just E tilde. So it makes this shift go away. And therefore, our new ciphertext is now, or our sanitized ciphertext is now statistically independent of R star. Good. So much for this basic technique to achieve circuit privacy. Now let's go into the refined tools. And in particular, I mean, we've already seen definitions of lattices, but for completeness, let's reiterate this. We take ourselves a full rank matrix B over R to the n times n, and it's all integer combinations of the columns of B is a lattice. There's, of course, alternative ways to define this, but good. An important object associated with a lattice is its dual, so-called dual lattice, which just consists of the all y in R to the n, such that any z in the original lattice, if I take an inner product with y, I'm going to get an integer, right? And alternatively, I can write this as a lattice spanned or generated by this matrix B inverse transpose, right? B is a full rank matrix, so it has an inverse over R to the n times n, and then I still transpose it, right? And sort of to see how I get from this definition to that one, it's kind of rather simple. I mean, I know that all the columns of B are in the lattice lambda, so I'm just collecting linear equations here. I'm setting up a linear equation system and solve it in the end for y, and then I'm going to get that every y has to be of this form, and the other way around is as simple. Okay, I wrote that I'm going to talk about Fourier transforms here, but then when I looked at the slides yesterday, I decided to sort of cut this out and instead briefly talk about singular value analysis, right? Come again? Why is the matrix transposed? Let me look at the time. We essentially have 50 minutes. It's good. We can actually, I mean, I said it's a simple exercise, but we can do this, right? So we know that all the columns, let's say B is something like B1 to Bn. Those are the columns of my matrix B. And I know that each one of them is, of course, in lambda, right? Because I multiply B just with a unit vector, the matrix B with a unit vector, and I'm going to get these BIs. And now you know that any given, let's say, Y in lambda S, it now holds that for all BIs that BI comma Y, this inner product is some integer, let's call it Ti, right? This is just from the definition of the dual lattice. And if you write this out, this inner product, just as a matrix vector multiplication, you get these BA transpose times y equals Ti. And if you do it for all of them, you just get matrix B transpose times y is this vector consisting of these T's. And if you solve it for y, you just get y equals B transpose inverse times T. Right? This is the reason why you have B transpose instead of B inverse transpose, sorry, instead of B inverse showing up there. Good. Okay, I have this. Good. Now let's briefly talk about singular value analysis. So give me any real valued matrix A in R to the n times n with, say, m greater than n. The singular values of this of such a matrix A, we call them sigma 1 of A until sigma n of A, and sort of typically or canonically we assume sigma 1 is the largest singular value, sort of as opposed to how this is done with short vectors in lattices, where lambda 1 is typically the shortest. The length of the shortest vector, and here these singular values are just the square roots of the eigenvalues of the matrix A times A transpose. Now you might ask, wait, does A times A transpose always have an eigenvalues, or is it diagonalizable? And the answer is yes. This is a positive definite matrix, and such an A can always be written as this is the, let's say, the singular value decomposition theorem says that A can always be written as U times D times V transpose, where U is an orthogonal matrix, right? It's just a rotation. V is an orthogonal matrix, just a rotation, and my D is a non-square matrix. So D has the same shape as A, but it's 0 everywhere and only on this hemi-diagonal you're going to see the singular values showing up. Okay, and I could quickly mention positive definite matrices. This is in fact right now almost everything we use about singular value decompositions. Matrix M is positive definite if it's symmetric and all of its singular values are positive, right? And as a shorthand, we just write M is greater than 0 for this. And any positive definite matrix can be written as A transpose A or A times A transpose, however you like. Alternatively, these positive symmetric matrices are like inner product matrices, right? This definition is equivalent to requiring that for all non-zero vectors x transpose times m times x is greater than 0, right? If you, for instance, how can you see that this holds? If you use this form here of M, then you have X transpose A transpose times A times X, and this is now just, well, A times X squared, right? The norm of a times x squared, and since all singular values are positive and therefore non-zero, this a times x squared is also non-zero, or is greater than 0 as required. Good, and as an additional notation, I write m greater than m prime if m minus m prime is positive definite. Okay, and now let's look a little bit closer at Gaussian distributions. Typically, a multivariate Gaussian distribution over r to the n, we denote by dr to the n square root sigma, where sigma, capital sigma, is now a positive definite matrix, which is a maybe slightly scaled variant of the covariance matrix of such a Gaussian. So if you really, a property that we're soon going to use, the expectation of x times x transpose, right? This is not an inner product, this is now an outer product, is just sigma. Good. So in a way, sigma completely characterizes a Gaussian distribution. So if you give me a Gaussian distribution, a continuous Gaussian distribution, I just have to compute the covariance, and I fully specified this distribution. So discrete Gaussians, we also heard about them already, are kind of the same thing over infinite but discrete sets, typically lattices, right? So a discrete Gaussian distribution has probability mass proportional to the continuous Gaussian function scaled down by the Gaussian mass of the entire lattice. Good. And they, in 2 dimensions at least, they look something like this. Okay, but now it's about time that I'm gonna talk about smoothing. So this idea of smoothing, as far as I know, was originally introduced in MR04, as Daniele said, to sort of blur a worst case lattice, and in that context it was introduced sort of just as a tool, as a complexity theoretic tool, to analyze the hardness of a problem which was SIS there in terms of worst case problems, SVP. So, but beyond this mere use as a tool to build reductions, it turned out to also be incredibly useful to build cryptographic schemes that have nice statistical security features and don't need to rely on drowning, right? I said drowning is undesirable for several reasons, that it forces us to use a stronger hardness assumption, and it kind of ruins the parameters. And in order to sort of quantify how much noise you need to smooth out a lattice, they introduced this parameter called the smoothing parameter, and we just say that sigma is in the smoothing regime or greater than eta epsilon of lambda if actually the Gaussian function with parameter 1 over sigma over the dual lattice is at most 1 plus epsilon. Since rho of 0 is always 1, it means all but epsilon of the dual Gaussian mass concentrates in the 0 point. Okay, but what So this tightly corresponds to a notion of discrete smoothing, but what I'm gonna use, or what I'm gonna look at, is some notion of continuous smoothing, which was originally proven by Regev. Let's say.
I have one question. Can you provide some intuition on the smoothing parameter, because the definition is complicated and
yes, I think this lemma here kind of is going to show you what's hopefully give some intuition on what's going on. So for this lemma here again, we're doing continuous smoothing, or let's say infinite smoothing here. Let's say sigma is greater than square root of 2 times the smoothing parameter. Now we're going to take ourselves a discrete Gaussian with parameter sigma on a lattice and an additional continuous Gaussian. And we're going to look at another continuous Gaussian, which is just has parameters square root of 2 times sigma. Then this smoothing lemma, this continuous or infinite smoothing lemma here says that x plus e, so the sum of this discrete Gaussian x and this continuous Gaussian x, e, is statistically close to this E star. In a way, it says that if you give me a discrete Gaussian here and add a continuous Gaussian on top, then this discrete Gaussian behaves like a continuous Gaussian, right? Because if I was to add 2 continuous Gaussians together, if x was a continuous Gaussian, I would get exactly the same. The sum of 2 Gaussians, their probability distributions are convoluted with one another or convolved with one another, would then just correspond to this slightly wider Gaussian. And what happens here? Let's look at a kind of a discrete Gaussian, right, convolved with a very narrow Gaussian. Right, so sort of the peaks here, this is the discrete structure that you're seeing, and I'm adding a continuous Gaussian on top, and of course this then corresponds to the convolution, right? So here, what you're seeing here is a convolution of a wide discrete Gaussian with a narrow narrow continuous Gaussian. So here, this Gaussian comb that we're seeing here is obviously far from a true continuous Gaussian. But what happens now if we're getting closer to the smoothing regime with our continuous Gaussian, right? Because the thing that's being smoothed out here in the end is the continuous Gaussian. So what if we make this parameter bigger, then you can see these peaks slowly blend into one another until at some point we get a really clean looking continuous Gaussian, right? So what this definition of the smoothing parameter in a way tells you is how much how wide do you have to make your continuous Gaussian so that let's say a similarly spaced discrete Gaussian, when you add it on top, really just behaves like a continuous Gaussian. And this let's say Fourier analytic definition of the smoothing parameter is really just a concise way of capturing this. Right? I mean, no time. I don't have time to go too deeply into Fourier analysis, but this is sort of what the smoothing parameter captures. right? So once you're in the smoothing regime, the discrete structure here becomes invisible, right? Statistically invisible. Good, but the technique that I'm going to use together with Regev's smoothing lemma is something I call Gaussian decompositions, and this is for now something just about continuous Gaussians. So give me any matrix Z. Think of Z as a short matrix, as a matrix with short entries. And now give me two continuous Gaussians, E1 and E2. So E1 is a spherical Gaussian. It just has parameter sigma 1. And E2 is maybe a non-spherical Gaussian. It has maybe a covariance matrix, maybe a more a wilder covariance matrix. Then if follows, we're going to see this in a moment pretty easily, if you take the first matrix vector product of Z and E1 and add E2 on top of it, right? You compute Z times E1 plus E2, then you again get a continuous Gaussian, this time with a covariance matrix sigma 1 square Z transpose plus sigma 2. And but you can do this conversely, so this was not a decomposition, so I'm basically composing E1 and E2 into this Gaussian E3, and conversely, if you give me an E3, right, with a covariance matrix of this form, I can decompose it into independent E1 and E2, such that E3 is Z times E1 plus E2, right? In a way, and this is really the magic of Gaussians, you just give me some E3, right? E3 is completely oblivious of this matrix Z, and I can just make this Gaussian Z times E1 appear out of this Gaussian E3, right? So E3 maybe knew nothing about Z, but all of a sudden, just by choosing this covariance matrix carefully, so there's still a so this sigma 2 has to be, or sigma 2 minus this thing here has to be positive definite, right? And this is the case if, for instance, sigma 3 is just of the form sigma squared times I. So this E3 is a spherical Gaussian, and in that case, such a covariance matrix sigma 2 always exists if sigma, which again is the parameter of the sigma 3 is of the form is greater than, here just as reals, than sigma 1 times the largest singular value of this matrix Z. And to look at the proof, really it suffices to compute the covariance matrix of my E3, right? So I'm computing the expectation of E3 to transpose, and now we use linearity of expectation, and we get these 4 terms here, and since E1 and E2 are independent, the expectation of their inner products is 0. So what remains is this Z E1 transpose and expectation of E2 transpose, but this is just sigma 1 squared times I, and this is sigma 2. So I'm getting this expression here for my sigma 3. So, and if this should be sigma squared times I, then I can always sort of find a matrix sigma 2. So in this case, I can decompose as if this matrix here is positive, or then this matrix sigma 2 is positive definite, which I can just base on the fact that sigma square is greater than sigma 1 square times, or sigma is greater than sigma 1 times sigma 1 of z. Okay, I'm not going to go much deeper into this proof, but what this Gaussian decomposition allows me to do is to come up with a sort of a Gaussian version of the leftover hash lemma, right? Recall that in the leftover hash lemma we had a matrix A which was uniformly random over ZQ. Now I want to do kind of the same thing over an infinite domain. What I want to say is fix some short matrix Z, and let X be a discrete Gaussian, right? A moment ago, X or E1 was a continuous Gaussian. So give me a discrete Gaussian and a continuous Gaussian, and now look at Z times X plus E. What I want to show is that not just X plus E is Gaussian. This would follow from Regev's continuous smoothing lemma. I want to show that Z times X plus E is Gaussian, right? And the way I'm doing that, concretely, X follows a discrete Gaussian. E, let's say, follows a wide enough continuous Gaussian. Then I get that Z times X plus E exactly follows a continuous Gaussian with covariance matrix sigma of this form. And sort of there's kind of a lot of text in the proof, but the interesting thing happens only happens right at the beginning, right? So I'm having this this term E, which follows a continuous Gaussian. And the first thing I'm going to do is I'm going to take this continuous Gaussian and decompose it via this lemma that we've just proven as Z times E1 plus E2, where E1 and E2 are independent continuous Gaussians of appropriate dimensions. And now I can just rewrite Z times X. Recall that X is this continuous Gaussian. Z times X plus E as, well, CX plus Z E1 plus E2. And now I'm having Z times X plus E1 plus E2. And now I'm at the point where I can use Regev's smoothing lemma to say that X plus E1, that's essentially a continuous Gaussian. Right, that's statistically close to a continuous Gaussian, and now I can kind of reverse all of this. So X plus E1 is now my X prime, and computing the covariance matrix of this, I'm getting this matrix here. And now that we've looked at these refined tools, let's look at how to do let's look at the main idea of how to do FHE circuit privacy with polynomial modulus to noise. So half an hour ago, we've seen how we can really, let's say, conceptually simply do that with drowning, but we get bad parameters for that. Now let's look at a slightly more involved strategy, which, however, gives us better efficiency and better hardness because we get better parameters. So recall from yesterday when Shweta introduced this, that the gadget matrix is essentially of this form, right? It's a tensor product of an identity matrix and these and such a powers of 2 vector. And she also introduced this randomized G inverse, which is essentially just a Gaussian sampler on the dual lattice of this G, right? So Shweta provided this short basis of lambda star of G, which is something of the form 2. Can I erase? Oh, 2 minus 1, 2 minus 1, 2 minus 1, and so forth, right? This G, or the lambda bot of G, has a short basis. Therefore, we can do Gaussian sampling over this lattice via, say, the classic GPV algorithm, and we just use the shorthand of G sigma inverse of C for any vector C to denote a Gaussian distribution on Z to the M with parameter sigma conditioned on G times X equals C, right? Conditioned to be in this coset of this lattice. Okay, maybe quickly. Good. And then let's look again at the GSW. Again at the GSW scheme. So Burs et al. Defined an alternative homomorphic evaluation function. Recall that in the vanilla GSW scheme, so it's rand, here I'm using an alternative notation, this should be sigma. Recall that the original GSW scheme just used C1 times G inverse of Z2 as to perform a multiplication. Here we're using this randomized G inverse, and we're adding a small additional error. So in the basic drowning-based scheme, this was a drowning error. In this scheme, it can be a much smaller error. So what we would like to show is that such a ciphertext C computed in this way is statistically close to a fresh encryption of M1 times M2. I can't show that for all components of this ciphertext, but let's maybe break things down a little, right? So what does this homomorphic evaluation do? It computes C1 times C rand inverse of C2 plus, but it adds nothing up here, and just in the last row we have this drowning error. And since this is kind of big here, I'm just looking at the first column of this matrix. It's going to be the same for all other columns. Good. So first off, let's say our ciphertext matrix C1 is again of this form A and SA plus E. Now this looks like a public key of GSW, but then again a public key of GSW is nothing but an encryption of 0. Right? So a GSW public key is just a 0 encryption, and I'm still having this payload component M times G. So if I now just look at a single column of the homomorphically evaluated ciphertext, I'm getting C1 times X plus 0, and if I write this out, I'm getting this A concatenated with this SA plus E times X plus 0 E tilde plus M times Z, right? When I multiply X with this M times G, X times G is just this C, but there is a technique necessary to deal with the C that appears here, but for time constraints, I'm not going to go into this, and just going to look at these first two components. Namely, oops, wrong button. No. Here. This A times X and this SA plus E times X. And A times X is up here, and instead of SA plus E times X, well, A times X is already there. I'm just going to look at E transpose times X here. And so first of all, via the leftover hash lemma, I get that A times X is statistically close to uniform. This additional information I get about X from this term can be just bounded with a min entropy chain rule, and I get that A times X is still statistically close to uniform, which is great. And in order to argue that this part here is essentially independent of E, I'm going to use the Gaussian LHL with the matrix Z equals E transpose. So this E transpose times X plus E via the Gaussian LHL just looks like a fresh Gaussian error E. And I've made this residual term disappear, right? So where I needed drowning earlier to get rid of this cross component here, I can now just rely on additional randomness provided by this X itself. Okay, but now let's quickly go into the last thing, namely entropic LWE. So quickly, I mean, I already hinted at this. What is entropic LWE? This is LWE where the secret S isn't uniform, but only comes from a high min entropy distribution. And you can think of this as a form of LWE which provides security even if an adversary gets some additional leakage on the secret. So again, in LWE, S is uniform. In entropic LWE, S only comes from an arbitrary from a high min entropy distribution, which could otherwise be arbitrary, right? So choose any sampler with sufficiently high min entropy, and here we still require the same thing as in standard LWE, namely that A and SA plus E is indistinguishable from A, uniform. Great, and the way to analyze this was, let's say by now the classic way to analyze this was introduced by Goldwasser et al. Via the so-called lossiness technique, right? The idea here is to use LWE itself to replace the matrix A with, here it is, the uniformly random matrix A by a matrix B times C, which is a low-rank matrix. Think of B and C as uniform plus F, where F now comes from the LWE error distribution. So, in fact, LWE allows us, just by a simple hybrid argument, to argue that such a matrix which is close, or this matrix here, which is close to a low-rank matrix in Euclidean distance, that this is computationally indistinguishable from a uniformly random matrix A. Right? And the cool thing is when we multiply A with something from the left side, it's uniformly random, it's going to be an injective function. Whereas this function here, if we multiply it from the right side with some random vector, it's going to lose information because, or with some say random, maybe short vector, it's going to lose information, right? So first of all, B compresses. If I multiply from the right side and then whatever C does doesn't matter, the only critical thing is F, right? But F is a short matrix and therefore also in some sense loses information. So and the GKPV just proved this or used drowning to argue that even if S comes from some min entropy distribution, that A, SA plus E looks like AU. And yeah, so S is chosen only from a high min entropy distribution. But in a first step, we can use LWE, as I just said, to replace A with BC plus F with such a lossy matrix. Okay, not a lot has happened, but now we can just multiply this out, and we have SBC plus SF plus E, and now if S is a short vector, comes from a short distribution, right? They asked S to be supported on 0, 1 to the n to be short, then you can say that S times F plus E leaks very little information about about S. This is a counting argument, and we can use the then in this case, SF is short, and E, if E is chosen wide enough, it just drowns out SF, and this should be the same E here. So if we have an E that's wide enough to drown, we can just drown out SF and just have SB plus C plus E prime, and now we're in the nice setting, this was the drowning step, that we can just use the leftover hash lemma to argue that this SB is statistically close to a uniformly random T, right? Because I chose S from a high min entropy distribution. SB, replacing this with T, is just the LHL, and once I'm here, I can just once again use LWE, this time with a matrix C instead of A, to argue that TC plus E prime is computationally indistinguishable from uniform, and now I'm just reversing this step of replacing A with BC plus F, and get and replace it with a uniformly random matrix A. So this is the classic way of proving this, and in a work with Zvika Pakersky a few years ago, we refined this using this smoothing technique, or this was kind of my first encounter with this idea of smoothing. So we introduced this notion of noise lossiness, where we said, give me any distribution S supported on ZQ to the N, not necessarily short, and give me an E which is Gaussian with parameter sigma. Then the noise lossiness of S is just the min entropy of, or the conditional min entropy of S given S plus E. So think of this as someone gives you S plus E, a noised version of S, and now you have to guess S. Right? And this is an alternative way to write this conditional min entropy. You're looking at the maximum over all guessers that sort of guess S correctly from a Gaussian noised version. And really, if S is like supported on such a set of points, we're adding Gaussian noise, and now the job of the guesser is to determine which. He gets some points somewhere, and he's supposed to determine which input point S he got, And for this simple case, the maximum likelihood decoder is just a Voronoi decoder. So in a sense, the noise lossiness models how much information is lost about S after passing it through a Gaussian channel, right? This sort of rephrases this problem kind of in terms of communication theory and asks sort of this source S that we're using, how bad of an error correcting code is this? Okay, and just quickly, we managed to compute noise lossiness for general distributions. Give me anything on ZQ to the n. If the distribution is sufficiently dense, you can argue that there must be a lot of overlap, and this distribution must have a high noise lossiness. So this is a generic way to compute this. Now, of course, if our input distribution S is forced to be short, then things are even better cryptographically speaking. So if the points are crammed in a small volume and then receive noise, then there's much more overlap. And accordingly, we get an even better noise lossiness. So in the general case, this drop here depended only logarithmically on n divided by q, and here it's sort of polynomial in square root n divided by q. So by making by sigma, by making sigma sufficiently large, we get a very nice noise lossiness. And to wrap this up, we sort of essentially implemented the same strategy as Goldwasser et al., however, with a slightly more refined argument. So the first few steps are the same. We replace A with this BC plus F and just multiply things out. But now things get a little different. Instead of saying that E drowns out SF, right, which was the strategy of Goldwasser et al., we say, no, let's take E and decompose it into E1F plus E2. And now we can rephrase this as S plus E1 times F plus E2. And once we're here, we can actually rely on noise lossiness. We can say that, look, no matter what the distribution of S was, here I'm having S plus E. So, and I know that sort of S plus E loses information about S. So I can now use the or loses a sufficient amount of information about S. I can now use the leftover hash lemma again to argue that SB is statistically close to uniform even given this S plus E1. Good. I do this via the LHL. And in the next step, I'm just going to in the next step, I'm just going to reverse this Gaussian decomposition here, right? I'm going to pull E1 back out and recompose it into E. And at this point, I can again just use the LWE assumption to argue that C, TC plus E, since E is sort of reconstituted, is computationally indistinguishable from uniform. This also makes this residual SF term disappear. And finally, I'm going to reverse this first step of where I turned A into BC plus F, and I'm done. Good. Okay, and that pretty much concludes my talk. So, I mean, I hope what I brought across is that drowning is a pretty general technique to remove noise artifacts. We've seen this quite a few times already in the summer school. But it comes with this drawback that it needs a rather strong LWE assumption and leads to practically undesirable parameters. This Gaussian smoothing technique that I've demonstrated here on two examples. First example being circuit privacy for homomorphic encryption. Second one being establishing security of entropic LWE. Is sometimes an alternative to drowning. So it's not a universal drop-in replacement. There are still some LWE-based constructions where we critically rely on drowning. As a maybe important example, threshold or multi-key fully homomorphic encryption with threshold reconstruction. So this is something where we didn't yet manage to find sort of a smoothing alternative to a drowning step. And this Gaussian smoothing really uses specific features of Gaussians, in particular this decomposability feature, and typically works with polynomial modulus to noise LWE, right? So here we're not just using Gaussians for underlying hardness reductions, but actually to establish statistical security properties. And we had some other recent applications. I had this work with Zwika Bakerski where we used this smoothing technique to prove entropic hardness of ring LWE, which actually no one had managed before to prove with a drowning step, right? So we could do something here in a regime with this smoothing where drowning seems useless. And finally, we had this construction of a so-called laconic encryption scheme, which is a simple type of laconic function evaluation, a concept that Hotek introduced yesterday, where which we could realize with polynomial modulus to noise ratio, whereas full-blown laconic function evaluation critically relies on drowning to prove security, to remove noise artifacts. And that concludes my talk. Oh, Shweta, maybe before yes, a question.
Yeah, thanks. Very nice talk. I was wondering if there is any kind of characterization that we can have. I mean, I know not formally, but you know, even just to understand the landscape, what types of applications will allow themselves to, you know, submit to this technique? Mm-hmm. There's also this other technique you must be aware of, like where you use Renyi divergence to analyze the distribution rather than statistical distance. And there also, in some cases, we can get polynomial modulus to noise ratio, but that also does not work everywhere. So do you think, like, you know, we have enough data points now to get a sense of what can work where, and what are situations where drowning still seems like the only way we know how to go?
Yeah, that's a very good question. I think the landscape is not fully charted, right? This is still interesting, interesting research questions we have here. So the main difference with, let's say, Renyi divergence based methods is, so what I've shown here typically works with any number of samples, right? So here you can crank up the number of samples, nothing gets worse. Whereas in the world of Renyi entropy, the bigger your LWE dimensions get, the worse things become. And I mean, it works for more general distributions than smoothing. Smoothing really relies on Gaussians, right, to do smoothing. But again, these Rennie techniques typically constrain you to search problems, whereas all I've shown here was directly working on indistinguishability or on decisional problems, right? So, I mean, my gut feeling is that that smoothing typically works well if let's say a secret you want to hide sort of comes from a Gaussian distribution and kind of contributes itself to hiding itself, if that makes any sense, right? So here we had this G inverse of X, for instance, in the Burs et al. In the Burs et al. Circuit private FHE scheme. So sort of something you want to hide contributes itself via its Gaussianness to hide itself. But by no means is this a conclusive picture, right? I mean, as I said, things like threshold FH or multi-key FHE with threshold reconstruction. So this is something that we tried a lot to get this down to polynomial modulus to noise, but so far with little success, because there it seems you're really. Okay, so here's maybe an additional take. So these distributions that I'm decomposing and recomposing, they all have expectation 0. But like in these applications where we don't manage to do things, if you go below a drowning regime, you can start measuring expectations of distributions. Right there, the drowning comes in to hide something which you can otherwise easily compute. Right there. I mean, here with this smoothing approach, I've done almost the same thing as drowning, just using a different analysis. Whereas the applications where we don't know how to do it, they are actual attacks, right? We would have to change the schemes.
Another quick question. So, like you mentioned that Rennie is more suitable for search than decision. This technique is not necessarily more suited to decision than search, right? I mean, we're just rewriting the error in a certain way, and it doesn't seem to me like this would do badly for search. Oh,
no, it works. I mean, decisional is typically the harder case.
Yeah, exactly. Right? So, I mean, did you try with things like threshold signatures or, you know, search-based applications? Because there are also those where you may want to try and reduce noise.
Yes, we did. But I mean, this is completely from a different angle. I think a lot of lattice threshold signatures sort of suffer from the secret sharing schemes involved, right? That like Shamir is our only good threshold secret sharing scheme, and Lagrange interpolation blows up errors. But that's a different construction side.
Okay, sure.
We have another question. Yes.
Can we return to a slide with fully homomorphic encryption circuit privacy?
Slide 34. What was it? I think I didn't have. How did you get the? How did you get the? Okay, 34. Let's see. Do you mean this one here?
I think a few slides more.
A few slides. Oh, you should say stop.
Sure. And stop here, and I think we missed it. The Sarit slide.
Come again? I'm already over it.
We just scrolled enough.
Come again?
Can we slide
back?
Forward.
Forward. Okay. Okay. You just say a loud stop. Here.
I think
so I had
more. I just looking for formula where stop. Oh, so my I think something here. So my question is about formula for C1.
Yes.
For example, we have A, which we masked with noise, and we have another matrix, which is M times G, and in this matrix, M is message, G is gadget, and point is that second matrix is, I think, G is known, and I think we could statistically leak some bytes of message. And my point is, should we mask MG in some way? Because MG is our information, is noise, and when we add A and when we add noise information, we possibly have some outliers.
So here I did something very lazy and potentially confusing, that I just wrote this ciphertext C1 as A S transpose A plus E. This A is not the public key here, right? I just say this is a random matrix. I should have probably called it U, right? This matrix here is of the, I mean, if you really write it properly, let's call this U, right? And this U is of the form A times R, where A now really is the public key, right? So This is just something very lazy that I quickly redefined for this slide A to be just a random matrix, right? But A times R, that is, I mean, even given the public key, is by virtue of the LHL, a uniformly random matrix.
Thank you. And I think little sub-question, should we MG mask in some way? I don't know.
No, I mean, this is masked by this A times R. So A times R is, this first part does look uniform to an outside observer, therefore it masks this M times G.
Oh, thank you, got it.
Okay, thanks. I think if you have more questions, or I think Nico will also be available later, so maybe you can take it offline.